Hello, welcome to my short presentation about some ideas how to do a double bracket flow on a quantum computer. So more specifically, I will tell you about a quantum algorithm. That quantum algorithm will be of a double bracket flow type. So I will tell you about double bracket flows, and that quantum algorithm will allow you to diagonalize, for example, the generators of your dynamics in a system. There's the QR code for the slide, and you can use it to click through the slides and then directly open the links by clicking. So there is one particular characteristic of the quantum algorithm that I would like to point out, namely the existing algorithms necessitate a large number. They strongly rely on controlled unitary evolutions. So controlled unitary evolutions we will be able to do on a fault-tolerant computer, but in existing architectures they are very tricky, and then the qubit that is controlling the rest of the circuit becomes a very sensitive point of the hardware, and that makes experimentally things quite difficult. So one way to think about it is that if we don't have to do them, something gets simpler. So that's one characteristic that will be present in the algorithm that I will tell you about. So there won't be any qubit overheads, there won't be controlled unitaries. You just need to evolve your system in an appropriate way. And that will give you a new approach to preparing useful states. It will allow you to build useful quantum algorithms, and you can also go away from the main topic that I will discuss today. I will tell you how to try to be even more efficient, and then how to use variational ideas to diagonalize different matrices even faster. So one thing that I will not talk much about is all the mathematics that is behind this proposal of the quantum algorithm, and I invite you to look at it, and I'm really happy to always talk about this as well. Okay, so there will be 3 ingredients to building that quantum algorithm. The first ingredient I refer to as dephasing, and the idea is that if you have a generator of dynamics, then you want to evolve under the dephased generator. That's one component that I will need. And here I'm only flashing a formula, and later the whole point of the talk is to tell you what that formula means and how to use it to build a useful quantum algorithm. So when I have this dephasing in place, I can use something called the group commutator, and that's a beautiful operation from group theory, actually, that you might use for Lie groups, but actually in quantum computing this comes into play for compiling. And if you want to think about a gate set being universal, so a set of operations being universal for quantum computation, you would be using this group commutator to create new interactions, new operations in the system out of the universal gate set. So that's something very fundamental for compiling quantum circuits. And finally, the algorithm that I will tell you about will be recursive. So a unitary at step k, preparing our diagonalizing circuit, will depend on the generators of the previous circuit. So it's a recursive prescription that I'm only flashing out here. And my point here is that it might be a little bit scary, but that's essentially all. With those ingredients, if you put them together in the right way, you get diagonalization. So we will be breaking them down side by side, and hopefully it won't be such a scary slide at the end. Okay, so goodbye, Homer, and let's get to work. To begin with, to tell you how to create this quantum algorithm, let me tell you a little bit about what condensed matter theorists have been up to in the 90s. And here, by the way, the professor here in the background is Rainer Dumke, and I will be working with him on providing theory support from my new fellowship at NTU in Singapore. So there are 2 openings in the making for quantum engineers who would be working with me on theory. So if you're interested and watching this around January 2023, let me know. So the quantum algorithm that I will focus on in this talk will be based on a particular double bracket flow, and it's called the Głazek-Wilson-Wegner flow. So the idea is that you have an input Hamiltonian. It's a symmetric matrix. So you want to diagonalize it. Okay, it's a Hermitian matrix. So we want to diagonalize this Hamiltonian H. And the way we will do it is that we will flow this input Hamiltonian. And the flowed Hamiltonian is defined as basically a unitary rotation of the input Hamiltonian. And the idea is that as the flow duration L goes towards infinity, then this flowed Hamiltonian curly H sub L will become always more diagonal. So we will have a diagonalization of our input Hamiltonian. So here we will achieve that using the GWW flow unitary, and that's a diagonalization unitary. So if we have a quantum algorithm that prepares the Głazek-Wilson-Wegner flow, we have diagonalization. So what is this GWW flow unitary? Well, it's of a special form such that the flowed Hamiltonian satisfies the GWW flow equation. So what we have here is a generalization of the Heisenberg equation. In this form, it looks like the Heisenberg equation, okay? Because I have the change with flow duration, maybe evolution duration, and that duration is related to the Hamiltonian, and you take a commutator with some operator. The difference from the Heisenberg equation is that it's a nonlinear evolution equation. It's a nonlinear prescription for the unitary, because at every stage the tangential direction to our unitary flow depends on the position where we are during this rotation of the flowed Hamiltonian. So this canonical bracket that is coming into play here has 2 ingredients. The first ingredient in the commutator here is the restriction to the diagonal. And the second, so delta for the diagonal, and then sigma looks like an O, is for the off diagonal. So the way you define them is basically you take a matrix, a flowed Hamiltonian at some flow duration, and then you just take out the diagonal. That's the diagonal restriction. Or you take that matrix and remove that diagonal, so you're left only with the off diagonal part. And when you look at the commutator of those 2, that's the direction, that's the generator of an evolution step during our flow. So that object here is called the canonical bracket. It is a bracket, a commutator. So this evolution equation is a nested commutator. It's a double bracket, so to speak. So this is a very special double bracket flow, and it's special because we have the GWW flow monotonicity. And let me explain what's going on here. So I'm looking here at the off-diagonal restriction of the flowed Hamiltonian. So as I'm flowing, I'm looking at the off-diagonal, and I'm looking at its magnitude as quantified by the Hilbert-Schmidt norm. Now, I look at that magnitude quantifier and I check how much does it change as I'm flowing forward. And with equality, this change is non-positive and just depends on the magnitude of this bracket. So when the diagonal and off-diagonal parts don't commute with each other very much, then we are flowing fast to become diagonal. That's the idea of this flow. That's how it's constructed. That's the power of this double bracket structure. It's very nonlinear because it achieves something quite complicated. So a diagonalization unitary is a very nonlinear function of the entries of the Hamiltonian. So that's why we have this nonlinear evolution equation here. But if we are able to prepare that, then we know that we will be decreasing the magnitude of the off-diagonal part always more as we go with the flow. So the rest of the talk is to tell you how to do it as a quantum algorithm. Okay, so let me first tell you a little bit about the structure of the operations that we will be implementing. And in the title, I say double bracket flow. This GWW flow that I just introduced is a special case of a double bracket flow. So in a double bracket flow, we consider a unitary transformation of some input Hamiltonian. And we want that it satisfies this generalization of the Heisenberg equation, namely that there will be a double bracket. And the generator of the flow, the evolution, will be maybe depending on the Hamiltonian that we are considering. And you do an operation A on that matrix, you get something. You do operation B on that matrix, you get something. You take the commutator of those two, then take the commutator with our float Hamiltonian, and that gives us this evolution equation. Now, what I told you about is a particular example where the A operation is take the diagonal of the float Hamiltonian and B operation is take the off diagonal, but you could imagine that you take something else. So for example, you could think of taking a variational flow. So what I'm proving in the paper is that you can also consider unitary rotations of the input Hamiltonian with a different kind of bracket where instead of a regular bracket, I just consider this operation here to be diagonal, okay? And I can always do this because for regular Hamiltonian evolution, we always have e to minus I t h. And now this I and h actually is an anti-Hermitian matrix. So as long as I take an anti-Hermitian matrix, this will be unitary. So now I said, okay, let me just choose this to be a diagonal matrix, and then let me just like take the commutator with h, and so the evolution will be again a double bracket, but it will be variational because I can choose this variationally depending on which one fits best for the particular Hamiltonian. So it's a different type of a quantum algorithm, again targeting diagonalization, but in a different way. So what I'm proving is a generalization of this monotonicity. So if I evolve this by S, then the initial decrease of the diagonal magnitudes of the couplings will depend on the actually projection onto the canonical bracket. So the canonical bracket, exactly as I was defining for the GWW flow, and it's canonical because it's appearing in this monotonicity direction. So if I think of a projection, as long as I'm projecting like this and not going in the other way where I would flip the sign, I will be decreasing the off-diagonal magnitude of the couplings. Okay, so it's a generalization because if I would do this evolution with the GWW bracket, I would get exactly the same thing here. And here I don't always get negative signs because the sign can flip, but then I can just flip the sign of this, and I found some direction, some way of diagonalizing my Hamiltonian. As long as this is diagonal, you just need to choose the right sign, and then you go. Okay, so that's quite a simple variational flow, and those variational flows are quite awesome for quantum technologies. People like them because people hope that we will be able to quickly start using quantum computers for the industry applications, for example. So here you can also use variational ideas, but in the rest of the talk, I will tell you about the continuous flow and how we can implement it on a quantum computer. So, okay, let's look at something similar. Let me take my input Hamiltonian here and create the canonical bracket. So take the diagonal of my input Hamiltonian and take the off diagonal of the couplings. That gives me the first canonical bracket of my discretization of the continuous flow. And then I just unitarily rotate my Hamiltonian. So, and then we ask, okay, what will happen? Yeah. So when I have this Hamiltonian, I can put this Hamiltonian again into this double bracket structure and create a new bracket. So I can always make a new step and recursively keep flowing forward. So that's a discretization of the continuous flow. And what I'm showing in the paper is that it actually is worthwhile to consider quite long steps, because what I'm showing on the off diagonal here is the magnitude of the off diagonal couplings, and they become minimum if I go further. So in the first step, I should be either here or here, that there's no big difference here. But in the second step, I will be taking H1 as my initial step because it's like recursive. And then for the H2, for k equals 2, I should actually take quite a long flow step. So if I do it many times, I have my first flow step, second flow step, and so on, I will be decreasing the off-diagonal norm of my matrix. That's how the Ising Hamiltonian on three sides looked in the beginning, and that's how it looks at the end. So in this example here, I'm actually showcasing that you can flow towards a non-diagonal matrix because of symmetries. So what we have is that we have the promise that the canonical bracket will be decreasing in norm, but it can start decreasing in norm if we just decouple two blocks. But here I have also true eigenvalues. So some subspace of the state of the system becomes diagonal, and sometimes I will have symmetry blocks where I also have quite interesting physics. That's not a big problem at all, because you can variationally add some perturbations to the flow and it will start fully diagonalizing. That's actually quite a special case because the Ising model is quite special. Usually you should expect that there won't be too many symmetries like that. Okay, so just to say this procedure, if I let S going to this flow step duration, if this will tend towards 0, then we will have pointwise convergence to the continuous flow that I was introducing, that is coming from the condensed matter. So condensed matter theory. So here everything works out okay. There's no problems here with the discretization. That's something that I'm proving in the paper as well. And after this comment, let me just mention, in the moment when I will tell you how I will do this with a quantum algorithm, I will actually not be speaking about HK, I will be speaking about JK, because I will have approximations to this recursive definition of HK. So HK plus 1 is defined, HK is defined through HK minus 1, because you can view HK as a rotation of HK minus 1 using a new updated generator. So you can always leapfrog forwards. It's a recursive prescription. So this is for the exact use of there's a typo here. There should be a K. That's for the exact use of the bracket. Now I will have something that approximates that unitary operator. So I'm speaking of this generator as being JK, and then I will again use it recursively. All right. Okay. So the quantum algorithm will aim to approximate that and not directly implement. That's why JK will be appearing for the quantum algorithm. Okay, so how do we do it? We want to evolve this input Hamiltonian under some approximation of the bracket here. And for evolving, so this is an evolution governed by a Hamiltonian. If I put an I here, that will be a Hamiltonian. And to evolve under such a bracket, we need to use this group commutator that you know from Solovay-Kitaev. compiling. And in the paper, I'm proving actually new bounds on the error here, and that error actually, interestingly, again depends on the canonical bracket. All right. So what is this group commutator here? Well, I have two ingredients here. So I need to evolve forwards with the diagonal restriction of the Hamiltonian. Then I evolve with the Hamiltonian. Then I evolve backward with the restriction, and I evolve backward with the Hamiltonian. And then you can see either from BCH, or if you want a better error bound, you can use a more general integral technique that is known in the literature. And then you see that the first order will cancel, and with S squared, I will have a unitary operator, a gate moving forward according to the commutator of those two operators. Okay, so I'm using H here because whether you have H or sigma, it's the same commutator here. So we get the bracket here. So the group commutator makes us happy as long as we can evolve according to the restriction of that evolution here, diagonal restriction here. So it's an evolution according to a restricted generator. It's not a restriction of the evolution. Those are two different things. So we need to have the diagonal restriction in the generator. All right. So now we want to insert this here, but we will actually be approximating it here. So actually in my quantum algorithm, I will be using an approximation to the group commutator using this approximation to the dephasing. So that one goes here, that one goes here. There's a dagger. That's why we have those inversions here, right? So this is replacing the exact evolution, but that gives me an approximation to the evolution under this constraint evolution. All right. So that is to say that if I can do this, then the dephasing implies that I have the group commutator. If I have the group commutator, then I can recursively go on. I will show this slide again, but basically now we will know how to implement this double bracket flow if we know how to do the dephasing. So again, the dephasing we need because the continuous definition of the flow rests on this restriction to the diagonal. And that restriction to the diagonal, it's a numerical procedure, you could think of it. Physically, it's dephasing. And in quantum information theory, it's known as a unitary mixing channel, which means that I have to take all possible independent phase flips on all my qubits, conjugate this Hamiltonian through these phase flips, and then normalize the sum of all those phase flips of the Hamiltonian, and that will be the restriction of my Hamiltonian here. Yeah, so that's a mathematical formula that I have from Watros's textbook, and I'm citing and describing this a little bit more in the paper. Physically, what it means is that if I have a state of qubits, then they might be somewhere correlated, they might be doing some other things somewhere else. And then in that formula, I have this index mu, which is actually telling me where I will be applying a phase flip, on which qubit in the system I want to apply the phase flip. So if I have a 1, I apply Z here, I will apply Z here, I will apply Z here, then here, and here not anymore, which means that you apply a local magnetic field and you wait for the correct time such that you will have a pi rotation of the qubit. So what happens if you do this? You can do this in many different ways, but what it will start doing is to dephase your state here and project everything towards the diagonal here. Okay, so in the formula, we have to do it in all possible different ways of choosing where the magnets go and applying them. Okay, so that's the formula in short. So basically, then I need to normalize by d the dimension of the evolution. I conjugate my evolution by those phase flips, and because those phase flips here are unitary, I can put them here. If I repeat it many times, I will get a summation here in the generator, and I will get an approximation to the evolution under the restricted operation. So our formula that we will be using is that this dephasing gate will be just an iteration of using those phase flips. And I'm also showing that in certain cases you don't have to use all possible phase flips. You can choose them at random, and actually you don't need so many in certain special cases. Okay, so that was quickly the dephasing. Once we have the dephasing, we are using it in two different ways: forward, backward, interlace appropriately with the actual evolution, and then we have the group commutator, and then we recursively say, okay, give me the k-1 generator. And once I have the k- generator, I can replace this generic j here by jk-1. I get jk here, and I get the group commutator here of jk. So I can keep repeating it recursively. There's a lot of arrows because it's recursive. That's the kind of non-linearity that is driving the flow. All right, so that was the quantum algorithm. Basically, you would need to write the directives, go do it this and that way. You would rely on regular computers to implement the circuit on the FPGA, and then what I'm showing in the paper is that's the way to implement that diagonalizing flow known from condensed matter theory. So let me show you some examples. So here we are on 5 qubits. And we can look at a variational example. So for the initial five steps, this Ising model on 5 qubits actually prefers to the fastest rotation is with the canonical gate, but at some point there would be asymmetries, so you need to start adding those variational gates. So second qubit gets a Z, fourth qubit gets a Z. You build the variational bracket out of such an operator, and then you go one step. In the next step, you put a Z in the middle. Then you put the Z on the left, and so on. So you just check for different ideas of the diagonal operators which to use, and the canonical bracket is maybe not preferred anymore here. If I have 7 qubits, then I have the canonical bracket, a variational bracket, a canonical bracket. And then at some point, actually, the canonical bracket is better than those diagonal gates. They are better in applications because they are much more cheap to implement than doing the dephasing, right? So that's kind of a difference here. In both cases, we see that the magnitude of the diagonal couplings is just decreasing downwards. So let me show you the comparison now on 3 qubits. Here I'm using only variational brackets, so in the middle, on the left, and you keep going down, and at some point I go towards 0. I fully diagonalize my state, and here I told you that the GWW flow is sometimes sensitive to symmetries, and so when I'm using the variational case, I see, okay, I start with some state that has a lot of energy fluctuations. As I'm flowing it forwards, the fluctuations are going away. So here I conclude I have an eigenstate, here I have an eigenstate, here maybe a little bit later, here a bit earlier, here a little bit later, here and quite early here. Okay, so those are the full eigenstates where I'm kind of getting into this regime where the off-diagonal norm is minimal. If I'm doing the GWW flow, then this is coming from equal superpositions of those two eigenstates. So it's actually not very bad if you get very nice superpositions of eigenstates, and that's also pretty cool. I don't think it's a big problem that sometimes this flow is sensitive. It's actually more costly in terms of the runtime that I will mention in a moment. So anyway, you will be breaking those symmetries just to be practical. But still, there is also value in having such persistent fluctuations being preserved here. All right, so that's a very simple example of diagonalizing on 3 qubits, but you see how fast it is. Like maybe even 5 steps is already enough to conclude that you have a very nice eigenstate in your system. Okay, so now a little bit bigger example on I think 11 qubits. So again, we have this behavior of the off-diagonal norm decreasing from a large value. It decreased quite a lot here already. What I'm trying to show in this plot is that actually, as the system becomes bigger, this norm, it's quite persistently big because the overall norm is big. So so maybe we shouldn't be worrying about epsilon bounds on the norm as measures for the diagonalization, because, for example, what I'm showing is that after 30 and 15 steps, the spectrum, the diagonal restriction of the float Hamiltonian almost perfectly agrees already with the true spectrum of the Hamiltonian. So here you have exponentially many values, but they just lie on top of each other. So and that was actually for 9 qubits, not 11. Okay, but already at 9 qubits, you have 500 eigenvalues and becomes quite dense. So maybe we don't need to worry about this so much and just heuristically cut somewhere here after 15 steps. Okay, so that was the spectrum. It looks pretty good. So let's look at eigenstates. So the flow progresses by sometimes lifting the degeneracies, and sometimes you get those huge energy fluctuations. That's actually a sign that is reorganizing the energy states. But what I'm showing here is that you get actually very narrow energy fluctuations around some initial state. So I take this product state, I apply 5 steps of the GWW flow, and well, okay, this is almost no energy fluctuations. I decrease the energy fluctuations, I narrow them down. So I could say, okay, that's my approximation to the eigenstate of the system. So maybe I'm missing still a little bit of energy that I could optimize downwards, but that's a quite cool guess for an eigenstate. You can also try to select eigenstates that have almost negligible energy fluctuation if you want to go towards this computational regime of having epsilon preparations of an eigenstate and not just physically saying, okay, that's low enough fluctuations in energy. I'm talking about energy fluctuations because it's an experimentally measurable quantifier for how good the float state becomes, how well it approximates some eigenstate. So again, in this procedure here, I take a product state as an initial state, and I'm showing the energy fluctuations that I get after flowing it for k steps here. Okay, if those energy fluctuations become negligible, then the flow of that product state becomes an eigenstate. That's essentially by definition of energy fluctuations. So I get very nice eigenstates if I apply it even for quite a large system. And now you could say, okay, so how much do I need to run this for a huge system when everything is, when the quantum computer will be powerful, you want to look at large systems? Well, I don't have a good answer for this because my analytical methods gave me scalings that are of academic value. The mathematics here is still quite curious, and I really enjoy thinking about this, but it's not of practical importance because the scalings are not very good. And the runtime is exponential in the number of steps because of the recursion, and in the system size because of the dephasing, for example. So the full scheme, the exact scheme that you would like to consider in computer science has a bad runtime in terms of the depth and number of qubits. Okay, so it's a big matrix. You could argue that it should be exponential in the number of qubits because it's a big matrix, but we don't really know the complexity of diagonalizing sparse matrices. So what else can I do? Actually, we should expect that it will be exponential. Well, if it's looking bad for the exact scheme, so maybe how about heuristics? So I was telling you about optimizing flow duration, flow step durations. That is helpful if you reduce the number of evolution steps. It's not necessary to simulate the bracket. You can also concatenate those group commutators only a few times instead of like very many times, and just repeating the group commutator only a few times already is allowing you to approximate the bracket quite well. It's possible to also take the first, let's say, 5 steps and say I times W is a Hamiltonian. I do Hamiltonian simulation as people are discussing a lot in quantum computing. And I just compile this Hamiltonian evolution with those generators. That gives me already an approximation to some diagonalizing matrix that will be much more efficient if you do it that way. The bottleneck is that you need to be able to compute those WKs to do the Hamiltonian simulations, so the classical control. You can use approximate dephasing. That's something that I'm bounding in the paper. But then one of the coolest ideas is to use variational brackets, which have much better scalings. It's just you need to get lucky how to choose those brackets. So each of them reduces the runtime, and I think the list can continue. So this algorithm can still be improved quite a lot if it receives more attention. Okay, so how does it work again? We have this quantum algorithm for diagonalization based on the double bracket flow. So the canonical bracket involves this delta operation restriction to the diagonal, and we do it by interlacing the evolution with phase flips. That was this dephasing that I was explaining in the middle of this presentation. Then those approximations to the evolution under the restricted diagonal restriction of the generator, we use those approximations D, and we interlace them with the evolution here. That gives us an approximation to the evolution under the group commutator. And then we keep repeating that recursively. I call this frame shifting in the paper. So I recursively evolve my my operator. So the JK operator will use the VK definition here, and VK differs from VK by +1 by recursively using that generator to use this group commutator as defined here. So again, a lot of arrows because it's recursive. If you unfold this recursion, then this VK will be just a concatenation of the group commutators, and each group commutator should be approximating the exact WK, the canonical bracket that you use for the Hamiltonian recursive relation. It's just that those are approximations, so I'm talking about JK, I'm not talking about HK because of those approximations, but the idea is that this is what it does. I'm showing that in the limit of S going towards 0, you get this equality that they are doing all the same. They are both converging to the continuous flow. So that's the idea. You use this canonical bracket always with this updated float Hamiltonian, and then you have your circuit, and as K becomes bigger and bigger, the idea is that we always better approximate the diagonalizing unitary. All right, so that is almost all, but there is more. So you can contact me if you want to chat about some new ideas of creating new algorithms, because I actually view this as a framework for building purposeful quantum algorithms. So there are also classical double bracket flows for linear programming, TODA flow, QR decomposition, sorting, matching optimization. Today I only talked about diagonalization, so that's one thing that I described in literature now, but you could think of going further. Okay, thank you.